Okay, welcome back to Advanced Applied Econometrics. Unlike previous weeks, this week I would like to start the lecture with a short summary of what we have done so far in order to motivate us a bit more into what we're gonna do now. So, okay, we started here where we have a sample of data of some dependent variables, y, with dimension n times 1 dependent variable with n observation. Then we also have some potential explanatory variables collected in an X matrix, again n observations and k potential variable. We sort of assume or determine that we would like to explain y upon x using some GLM model, generalized linear model. So then the model has form y equal to x times a set of parameter b plus epsilon. Nothing new over there, and then we have seen that we could derive the OS estimator, which is the mantra b equal to x prime x inverse times x prime y. Then we arrive to the equation y equal to x times b plus e, with b is the OS estimator, e is the estimated residual for the epsilon, and then the predicted value or estimated value of the dependent variables collected in x times b. We also know that the unbiased estimate of the variance of the residuals could be calculated as 1 over n minus k times the sum of square residual from our regression. Now, that's so far so good here. Then we have also looked at the Gauss marker assumptions. First say that, okay, the average error should be 0, expected to be 0, A1. The residual are error term and explanatory variable x's are independent, A2. And finally, A3 and A4 collected in the covariance matrix of epsilon, which is given by a constant sigma times an identity matrix of dimension n, right? So we will go back to this shortly after this. So far so good. Then with this assumption and this rule of estimating our estimator, our OS estimator is blue. Best linear unbiased estimator. Up to here. Perfect. We have a good and simple, understandable estimator for the interested parameter beta that we wanted to discover. However, we didn't stop there. We also came to the expression for the covariance matrix of B. So B is a set of parameters or coefficients. So they have their variances. They also have the covariances between different coefficients. So this covariance matrix of B is given by sigma squared times x prime x inverse. And because we don't know the variance, in reality we replace it with the estimate version, which is here, right? As we all know. Here it may turn a bit itchy already. Why do we have to know this messy thing? However, bear with me now. Don't just stop at the blue expression and life's beautiful. Now, bear with me. Then, at some point, we also willing to make an assumption about the shape of the distribution of the residual or the error, which is given by a normal distribution, which means 0 from this, and the variance, covariance matrix, sigma squared times identity matrix of n dimensions, A3 and A4. So all we do here is adding the shape of the distribution, which is the normal distribution. Thanks to that, we can also accept an assumption or make an assumption about the shape of the distribution of the coefficient, the beta, the sampling distribution, remember? There we assume that B, if error term is normally distributed, then B can be assumed to be also normally distributed with mean beta, because it's unbiased, we show that. And then the variance, covariance matrix given by this guy, right? But why do we care about the sampling distribution of B now? Because we did also hypothesis testing, right? Namely the t-test, the f-test, also sometimes you may have heard already the word test. We haven't addressed it explicitly here, but hopefully we'll come back when we have time in the next week. So now, the test statistic for these tests under the null hypothesis, some null hypothesis that we formalized, were derived based on this covariance variance matrix of B. Now, so therefore, after having that test statistic, you can conclude something about your hypothesis. So the point here is, if you just care about the marginal effect of X on Y within your data sample, let's say you interviewed 20 consumers in the supermarket Edeka on the 1st of April, and you just want to discover some effect of some explanatory variables on their buying decision in Edeka. No more, not generalized for other consumers in other supermarkets or other days, then you can stop here. Life is good until here. I let you go, you can go. Nevertheless, that's rarely the case in economics, right? When we do, when we collect data, collected in this data set, we usually want to make some conclusion that can be generalized for a larger population underlying this data sample. So you want to draw some conclusion to learn something about the behavior or the decision of buying something in the supermarket for a population of buyers or consumers somewhere else, maybe in Germany. And if that's the case, we need the hypothesis testing or somewhere. You could also see the term statistical inference. So make a conclusion about the underlying population based on a sample. So we have talked about it, okay, just because it's not possible or not recommendable to take the whole population into calculation, therefore we have to rely on a sample. So at the end, if we want to generalize what we find within this sample for a population, we have to do hypothesis testing. And there we need all the way down from here until here and until here. So you see, these Gauss marker assumptions are important, crucial, essential for deriving the covariance matrix of B. It involves all kinds of things, the sigma square and other things, also the distribution shapes. Therefore, it's important to have a look at what would happen, what the consequence for these steps if one of or several of these assumptions violated. And that's what we're going to do in the next week. In particular, this week, we will look at this one, A3 and A4. What is the consequence if the assumption about the variance covariance matrix of the error term are violated? Okay, let's first look at the variance covariance matrix of the error terms again. So now we know that the covariance matrix of error terms given by the expected value of epsilon times epsilon prime. the vector. And there we also learned it already. So at the end it will collect the variance on the main diagonal. So here, 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 right, are the variances. And everywhere else of the main diagonals are the covariances of different error terms. Alright? And under the Gauss marker assumptions A3 and A4, sorry, the covariance matrix of the error terms given by sigma square, a constant sigma square, times an identity matrix. If you don't have much impression about it, I would recommend going back to the video previously I made about this, right? And there under these assumptions, we have sigma square, this constant, the same for everywhere on the main diagonals, meaning the variances of different error terms are the same, constant, while the covariance of different error terms are 0. Let's write it down. So the first thing, let's use another color. The first thing is the variance of EI, epsilon I, equal var of epsilon j for all I different from j in k, sorry, in n observations. And the second one is the covariance of epsilon I and epsilon j equal to 0 for all again. So that's the Gauss marker assumption. So therefore, these are two assumptions, right? Because of that, it can be violated in two ways. The first way is the variance difference. So var epsilon I different from var of epsilon j for some I different from j in n. So doesn't have to be for all, but at least for several. Like for example, the variance of the first error terms different from the second one, or some groups of variance different from the other groups. Then that is already a problem. So this refers to heteroscedastic city. You must be exposed to this to some certain extent already. And the second one can be violated in a way that the covariance of, let's see, j, epsilon I and epsilon j different from 0 for some I different from j again. So some of these elements of diagonals will be different from 0, saying that the error terms are somehow autocorrelated. So this is autocorrelation. And these are the two diseases from the covariance matrix of error term that we will look at this week and see what's the consequence. Now let's start viewing the slide from here. Now what happens if there are autocorrelations or heteroscedasticities in our error terms? One important thing to remember is the coefficient from the regression, the b that we estimate, is still unbiased. If you go back to the video where we have worked on proving the unbiasedness of the OS estimator, you will see that we only used assumption A1 and A2, and we didn't touch A3 and A4 for that. Therefore, violating A3 and A4 doesn't affect the unbiasedness of the estimate. However, because the variance covariance matrix of the error terms will be used directly to calculate the variance covariance matrix of estimator B. Remember, then once this assumption about the variance covariance matrix of error terms no longer holds, then we cannot have the minimum variance or the least, the most efficient estimator anymore. Therefore, we can do better with estimating the parameters using other rules, other estimators rather than OLS. So that's the point. Now, moreover, as I have pointed to you several times now, we needed the standard errors, which is the square root of the variance of the coefficient, right? For hypothesis testing, closest example is the t-test. Yeah? And in the case, this statistical inference or hypothesis testing will be misleading. Okay, now we're back to the board because I want to show you something on slide 7. So in a more general way, we could write the variance covariance matrix of error term as a common factor sigma square times matrix sign. So meaning we could factor out a factor sigma square. It may or may not be the same as the sigma square that we talk about when we talk about Gauss-Markov condition before. Now the variance the variance of the error term. Now just a common factor. Now, and the generalized term here may be interpreted as the way we write this matrix, the Greek letters called psi. And depends on how the structure or the elements inside the psi look like. We may have heteroscedasticity or autocorrelation. Let's write down it so that you see that it's actually quite similar to what I show you with the variance covariance matrix itself. So here we have psi 1, 1, then psi 1, 2, all the way to psi 1, n, and here's psi 2, 1, psi 2, 2, to psi 2, n, and so and so and so, all the way here to psi n 1, and here you have psi n n. Now, so first of all, it's a square matrix. Why? Because the variance covariance matrix is a square matrix. So if you factor out a scalar, something, a value, the matrix remains square, this type matrix. Now, then, if we have psi 1, let's write it general, psi ii, different from psi jj, for some I different from j, then we have heteroscedasticity. So similar to the covariance matrix itself I have before. On the other hand, but note here now, so the variants are different for different observations. However, the off-diagonal elements still 0. So that's heteroscedasticity. On the other hand, if you have psi aj different from 0 for some I different from j, then you have autocorrelation, right? That's the first thing. So writing it this way could mean that either you have autocorrelation or heteroscedasticity. The next thing is psi is a positive, definite matrix. What does it mean? What does it mean? Positive definite matrix. No? So a square matrix A, so here I abbreviate as PD, is PE if x prime times A times x larger than 0, positive, for all vector x except null vector. You know what null vector is? It's the vector with all elements 0. Now, so of course, if you multiply it by all zeros, then you get 0. Nothing to say. However, if it's any other vectors that you chose and you multiply this way, the product is a scalar, no? That's larger than 0. Why it's a scalar? I could show you here. No. So let's say x is n times 1, right? So x prime would be, 1 times n, and in the between you have a with dimension n times n. No? Then this n will gradually be cancelled. No? Right? So at the end you have a scalar. And that scalar is larger than 0, and A is positive definite. No? So the property of PD matrices, first of all, the determinant, usually determine like the determinant det of A is larger than 0. Second of all, it's invertible. The next one is it has non-negative element on the main diagonal, right? And it's symmetric. That is hopefully familiar to you. No? So from this definition, by construction, covariance, variance matrices are positive definite. Therefore, if you factor out just a common factor sigma square positive out of the matrix, the remaining matrix, the resulting psi here, because you've just factored out from a variance covariance matrix, the psi must also be positive definite, right? This matrix, this positive definite matrix is very important in statistics. You will see it more and more. And also, if you remember, it was shown also very important in optimization, especially if you remember the second order condition. Okay, so the idea here is you have a general issue with the variance covariance matrix of error term like this, and it's not identity matrix like before. And so you wish to transform in some way this variance covariance matrix again to sigma squared times in, right? So it meets or satisfies the Gauss marker assumption A3 and A4 again. And in the next slide we will find a way to transform this matrix in so-called generalized least square estimator. Okay, having said that, let's see what we can do with the matrix side. The first thing to know is for any positive definite matrix such as psi, there will be a square non-singular matrix P. Square, you know that already, but what does non-singular mean? It means there's no linear dependency between the rows or columns. So the multicollinearity last week we talked about was one reason for non-singular of matrix, which make it hard or not possible to invert. Okay, back here. Then you can write the inverse of matrix psi as the inner product of the matrix P. Remember, I mentioned that this is the inner product. So P prime times P. Okay. Let's go further. Therefore, we would have the matrix psi itself is the inverse of the product of these two matrices. So the inverse of the inner product of P. But based on the rule of matrix inversion, I think it's on slide 27 of section 1 and 2, you can take the inverse of each matrix separately. Nevertheless, have to switch the order. So P inverse comes first and then P prime inverse come later. Then the next thing we can see is that if now we pre-multiply P and post-multiply P prime to the psi matrix, and we plug the impression of psi in here. Now this is psi, like follow from above, right? We get an identity matrix. Why identity matrix? Because the product of a matrix with its inverse is an identity matrix. So here you have I. The next one you also have I, and the product of the two identity matrix in turns another identity matrix. At the end you get I. Can you already have a feeling what we're trying to do here? No? Because remember, we would like to have something that satisfied the Gauss-Markov assumption, sigma squared times I. No? And we have sigma squared times psi now. No? So what we're trying to point out here is there's a way to convert the sigma squared times psi back to sigma squared times I again. If it's not that clear yet, then don't worry. We see next slide. The way to go now is to pre-multiply the matrix P into the original model. So P both left side and everywhere on the right-hand side. So you could write it as y star equals x star times beta plus epsilon star with y star here equals P times y, x star, I don't know why I always make that mistake, equals P times x, and then epsilon star equals P times epsilon. And this is so-called our transformed model. All right. And we could, I jump ahead a bit, try to apply OLS to this transform model and see what happens with the variance covariance matrix of zero term, because that's all we're concerned about. Before that, the original model violated that. Therefore, we could write the variance, see the variance of epsilon star now, the transformed epsilon. And plug it as P times epsilon in. And what would we have? Y here. Let's stop here a bit. Remember, during the statistic review, we have the variance of a constant A times a random variable X would be A squared times the variance of x itself. No? And in the matrix universe, there's a way to write it. No? For a matrix vector, it's like that. No? Pre-multiply p and post-multiply p prime. No? Does it remind you something that we did in previous slide? There we go. Okay. And we could write it again there as p, let me write it here, times the variance of epsilon. Before we have sigma square times psi, right? The DC that we have is collected in psi, okay? Then times p prime. Now, but because sigma square is a common factor and somehow a constant, we could write it in a way that sigma square comes first, and then p times psi and times p prime again. No? And we know from previous slide that this is an identity matrix. No? There we have sigma square times I again. And that means that the transform models again satisfied the A3 and A4 assumption from Gauss-Markov assumptions, right? So what's the key message? So the key message here is that if we know how psi, the matrix psi look like, no? We know what's the DC in that matrix of variance, covariance of the original residual, then we can transform the data using the factorization of its inverse. No? So that the transform model is healthy again in terms of covariance matrix of error terms, no? Given that we know the matrix psi. Okay, now that we know that OLX works for this transform model, we could go ahead and derive the estimator, no, for the beta using this transform model. No? Let's rewrite it again. X start as px and y start as py. No, px. Let's write x here. Therefore, x prime, x star prime will be px prime, right? And again, that means x prime times p prime. So you transpose each matrix inside this product separately, but have to switch the other. The next step, we have x star prime, times x star would be px prime times px, right? And block the one above in here. So that would be x prime p prime, right? Times px. Now, think about it. So p prime times p is psi inverse, right? So it turned out to be x prime psi inverse times x again. How about x star prime times y star? It would be px prime times py, right? And again, plug in px prime in here. X prime times p prime times p times y. And similar like above, we would have x prime psi times y, psi minus 1, psi inverse, So plug everything in here, you would have this expression. No? So x prime psi inverse x, everything inverse times x prime psi inverse y. Okay? But why can't we write b over here? like before, because the rule of estimation is now different, right? So it's no longer our OS estimator, even though we still applied OS to the transformed model, but it's another rule of estimating already. So here there's the beta hat also denoting an estimator for beta, even though the beta we didn't transform, we just transformed the data now. However, it's another estimator. So you have to keep that in mind. The properties of GLS. What properties does it have? So think about it again. We applied at the end OS to the transformed variables, right? We didn't transform the coefficient at all. The beta remained until the end. Therefore, the estimate of the coefficient will be the same as the original model. That's the first thing to keep in mind. The second thing, all we wanted to do by transforming the model was just to overcome the violation on the DC of the variance covariance matrix of the error term. Yeah. And this, as we have seen, was successful at the end. And because of that, the estimator again becomes the best linear unbiased estimator. Now, unfortunately, in reality, psi is rarely known. So we would not be able to know exactly what elements there inside the psi or what the DC is. Therefore, we need to estimate it first, just like we estimated the variance and other things that we have seen up to now, right? Then we could replace the psi by its estimate in the estimator beta hat GLS now. And this is called estimated or feasible GLS in the literature. A lot of times you will see FGLS. This estimator is not blue anymore. Why? Because we cannot guarantee 100% that the psi hat or the transformation that we applied will use exactly the Gauss-Markov assumption again. But at least we could expect that it will be consistent as long as the estimate for the psi hat is consistent. Remember what consistent means? Meaning if the sample size increases to infinitely large, then we could expect that the estimated parameter will converge to the true parameter. So that is the idea behind using GLS